Jai Hind to all of you. I am Dr. Ritish Kumar, going to give the lecture on the topic of Klystron tube. So, which lie in the subject of microwave and radar engineering. So, this is a very important topic. So, let's begin the topic of Klystron. First, we need to understand what are the limitations of conventional microwave tubes. So, why we go for the Klystron tube here? So, firstly, if I talk at the low frequency, there is no effect. There you will not get any kind of interelectrode capacitive effects. When we move towards a very high frequency, you will get the effect of internal capacitance. So that's why we call there are some kind of limitations at very high frequency. The first one is the interelectrode capacitive effect. The second one is the lead inductance effect, and then electron transit time, then gain bandwidth product. So first, what is the interelectrode capacitance? So if I draw the general diagram of a tube, it has one cathode, one grade, and one is the anode. So once one is the anode. So what is the interelectrode capacitive effect at high frequency? You will get you will have the capacitive effect in between these two electrode, that is in between gate to anode, then another is in between gate to cathode, other one is anode cathode, right. So these are the capacitive effect you will have at very high frequency. This one is written GA, GK and AK, right. So you can see what will happen at very high frequency. So if you talk about the reactance of this capacitance, that is Xc is equal to 1 upon J 2 pi Fc. If you increase the frequency, then you will have the reactance is very low. So if I say at the output side, so if the capacitance is very low at very high frequency, it acts as a very short circuited. So all the output passes from this short circuited path. You will get nothing at the output. That is the effect of the interelectrode capacitance, right. So it degrades the performance of conventional microwave tubes such as triodes, pentodes, etc., right. So next is the lead inductance effect. So what is the lead inductance effect? So apart from it, how we can minimize the interelectrode capacitive effect? So you know the capacitive formula A epsilon by D. So this is the D. You can say the distance between these two plates is D. So you can reduce the interelectrode capacitance effect by increase the distance between these electrode, or by taking the very small size of electrodes. If you take very small size of electrode, then you can reduce the interelectrode capacitance effect, or by taking the large separation between these two electrodes or these two cathode or anode, then you can also reduce the interelectrode capacitive effect. Now the next point is the lead inductance effect. So every wire has some inductance as well. So this kind of inductance you can see, right. This is a Lg you can write, this one is Lk you can write, and this one is La you can write, right. So So if you apply the input at this point, then you will get some kind of voltage here. So if suppose what should be the reactance of this inductance? So you can say L is equal to 2 pi f L, XL is equal to XL. If you increase the frequency, then you will have XL is very large. So at high frequency, the voltage drop is very high at very high frequency. That's why the gain of this tube will become degrades. So also we can say the lead in the inductance of lead also affects the performance of the tube at very high frequency. How we can minimize the lead inductance effect? So either you can take the very short length of wire, so you can minimize the inductance effect by taking the short length of lead or wire. Now the next point is next point is electron transit time. So electron transit time is nothing but the time taken by the electron to travel from cathode to anode. So this time should be as low as possible to make the device as fast as possible. I hope this what should be the condition to have or to reduce the electron transit time? So we know the concept of kinetic energy always be equal to the potential energy, right? Kinetic energy always equal to the potential energy. So kinetic energy is kinetic energy of electron is half mv square is equal to q into v. So v is equal to twice ev by m square root of, right. So in terms of, if I say transit time is equal to tau, so tau is equal to b by d, right. So b by we know the b by d. So we know the d, that is v upon square root of twice Eb by right. So by reducing the distance between cathode and anode, we can improve the electron transit time. So this is the matter how we can achieve the low transit time. The gain bandwidth product, the gain bandwidth is another limitation of conventional tube. So in the gain bandwidth product always be constant for the conventional tube. So if you improve the gain, you will have to sacrifice the bandwidth of the device. Otherwise, if you improve the bandwidth, you have to sacrifice the gain. So that is the limitation of conventional tubes, and to overcome these all the limitations, we move towards the Klystron tube at very high frequency. So this is the Klystron internal architecture of two cavity Klystron amplifier. How it works, how how at what principle you are using here. So we need to understand. So this is a construction of internal architecture of two cavity Klystron amplifier. You can clearly see here this is a cathode, anode, and this is a RF cavity. This is a RF cavities. Here you are using two RF cavities, as name suggested, two cavities. So first both are looking like similar way. So this one is the we can say we call buncher cavity, and this one is the catcher cavity. Why we call buncher and catcher cavity, we will learn further. So because it is at the input side. That's why we call buncher cavity as an input cavity, and this one is the output side, so we can say catcher cavity as the output cavity as well. And you can clearly see here, this is a drift space and this one is the collector, right? So this part is known as electron gun. Electron gun contains electron gun, right? So you can see here you are applying the RF input with the help of this buncher cavity, and you are receiving the output with the help of this catcher cavity. So this is a cathode. Once you apply the input at the cathode, the electron beams generated through this cathode and it is scattered towards the collector side, because if you with the help of this anode terminals, we are able to focus this electron beam to focusly towards the collector side, and it electrons beams passes through this buncher cavity. So if you don't apply this buncher cavity and catcher cavity, these electrons uniformly move with the same velocity towards the collector side, right? So with the help of this buncher cavity, if you apply the RF input, and we know that RF input is a very high frequency input, so RF input has this kind of signal, right? So it has plus polarity, negative polarity and zero crossing as well. So you can see here, if you for the positive cycle, for the positive cycle input signal, this electrons because electron has a negative negative charge, so for the positive supply it will get attracted, so electrons beam becomes faster at this positive half cycle, and for the negative half cycle electron charge electron repels from this inputs. So electron velocity of the electron degrades, and if you for the zero crossing, there is no effect on the velocity of the electron. So you can see that you can control the velocity of the electron with the help of this input cavity or buncher cavity, right? So you will see the effect of the velocity in the drift space, and because the velocity you are having in the drift is different for different electrons. So that's why we call this process is the velocity modulation process. As similarly in the case of communication system, for the amplitude modulation, the amplitude of the carrier signal varies in accordance with the instantaneous value of the message signal. Similarly, the velocity of the electrons modulated with respect to the applied RF input signals. That's why we call the process which we are having in the drift space is the velocity modulations of the electron, due to which some electrons move faster and some electron does not have any effect, and some electrons have slower. So faster electron capture the slower one and unaffected velocity of the electron. So that's why you will get the bunch of the electron here. As we know, the single electron has some energy and bunch of the electron has the more energy compared to the single electron, and bunch of the electrons of the energy gets released through this catcher cavity, and whatever the input you are applying at the input cavity, you will get the amplified output of the input signal. That's why we call this is a amplifier, right? Because the bunch of the electrons gets released more energy. And you need to understand here whatever we are whatever the process, whatever the change you will get only in the drift display with the help of buncher cavity only. So this space is known, this separation is the very important to modify the velocity of the electron. Okay. So the main concept of this two cavity Klystron amplifier is the velocity modulation. This is the main term, main logic, main principle of this device. If somebody asks what is the principle of the two cavity Klystron, the principle is nothing but the velocity modulation of the electron beam. That is the main principle, you can say. Now this is a these all the points I already discussed in the last slide. You need to understand here. This is the applied RF input signal. This is the transit time that I had discussed. So transit time for this input cavity is nothing but T1 minus T naught. Tau is equal to T1 minus T naught, and the distance is d and velocity is v naught. So this is the d by v naught is equal to T1 minus T naught, and you can directly the value of twice EV by ml is nothing but 0.593 into 10 to the power 6 square root of v naught. So you can clearly see here this is transit time angle, that is theta is equal to omega tau. We know the formula of tau, that is transit time, and we have omega d by v naught. This is nothing but the average value of applied RF signal. So average you can get by taking the one time period tau T naught to T1, and you will get the final equation in terms of sinc function. This is nothing but the sinc function, right? This part is nothing but the sinc function, right? This is nothing but the sinc function, right? So you can clearly see here. So how you can so here we are representing this term is a beta I. Beta I is nothing but beam coupling coefficient of the input cavity. This is nothing but the beam coupling coefficient of the input cavity, right? So as we know, if you make it kinetic energy is equal to potential energy, we have the formula of B is equal to square root of twice EV by m. Because we are applying the RF input signal at the input cavity, so this equation becomes twice E by m and B plus average of RF input signal, right? That we already know. So by putting the value of average value of RF input signal that we had calculated in the last slide, that is beta I V1 sin omega t naught plus theta g by 2, and if you take the common of v naught, it looks like as a similar equation of AM that we had read in the communication system subject. So this is if you remember SAMT, this equation of amplitude modulation is AC 1 plus KAMT cos 2 pi FCT. So this is the AM equation. If you compare this equation with this one, this is looks like similarly. So this is a modulation index KA mod of MT is known as modulation index. So here the depth of modulation, we are having a beta I V1 upon V naught, where V1 is the RF input voltage and V naught is the applied DC voltage at the Klystron tube. So we can say this is a depth of velocity modulation coefficient, a modulation index of velocity, velocity modulation index we can say. So it has two expressions for if you apply the binomial expression for it, so to the value of half power, so you can take it 1 plus nx here. So v naught 1 plus n is equal to half here. So beta e v 1 twice v naught sin, it comes like in this way, right. So alternatively we can write this equation in terms of T1 as well. You can see what is the T1. T1, so this is T naught plus theta g by 2. In terms of T1 you need to take the subtraction of it, right. This is omega T1 minus theta g by 2. So you need to understand this plus sinus becomes into the negative sign. If you write in terms of T naught, it comes positive, and if you write in terms of T1, it comes negative. Alternatively we can write. So this is the velocity equation after modulation process we are getting in the drift space, right. So this I already discussed here. The effect on the velocity is null. The electrons getting, the velocity of electron getting slower and faster, and at some point you will get the bunching process in the drift space as well, that I had already discussed in the last slide. I hope this Klystron tube is clear to all of you. So somebody, if somebody asks you what is the main basic principle of Klystron tube, that is velocity modulation, right. So I think this topic is clear to all of you. Thank you.